All right. So what is this? You might be able to guess. This is one screenshot of the suggested friends in Facebook, right? So one screenshot of friend suggestions in Facebook. Uh, okay, yeah. So it's a social network, and the task is, suppose we need to suggest friends. Now there are of course several factors a social network considers to suggest friends. But in this particular case, we will take something simple, which is actually also a very important one, that is number of mutual friends. Also, you can see that Facebook considers that as one of the important criteria. We'll later on study the locality property of social networks in later in the course, and we will see that this is actually one of the important criteria. So, so suppose if we want to compute a list of suggestions as friends, what could be a reasonable criteria? A reasonable criteria can be if X and Y have at least 3 mutual friends, then we'll suggest Y as a suggested, I mean, as a friend of X, or the other way. Can you all please go on mute? So somebody is talking.
That
People
not
are.
always means that আমাদের সময় ওইটাই যে সব সময় বেড়ে যাবে এটা না পেলে
Hello.
অনেক সময় ওইটাই লোকে চেয়ে বসে that not always means
Arnav.
Hello, who is talking? Please, can you go on mute?
Sir, so can we consider locality as one of the criteria for suggesting friends? I mean, for example, I may have 3 friends in common with a person in USA, suppose. So, will he be preferred over my friend in India?
No. So by locality, it's not a geolocation. The locality property of a network is what it means is that who is connected to who. Okay, so if you are connected to, so if A is connected to B and B is connected to C, then the probability that A and C are connected is higher than any two random people. So that is the locality property. Okay, so it's not about whether where you are living, it is more about the network. So what, so there are many kinds of networks. Okay, in every social network, it can be a Facebook kind of a network, it can be a telephone network, who talks to whom, it can be whether you work together with someone, so all those things. Okay, or you know someone professionally, somebody is your colleague or classmate or something. So there are many kinds of networks possible. Usually most of the social networks have this property. So we will come to this later in the course. As of now, this example is just to motivate rather an algorithmic problem that we want to solve using MapReduce. All right. Okay, so so suppose if X and Y have at least 3 mutual friends, and if they are not friends already, then what we would do is we will suggest Y as a friend of X. Suppose this is what we have defined as the problem. We are not considering whether this is the best way to do it, but this is one of the good ways to do it. Then our main goal here is, given a simple way to store the data, or the most obvious way to store the friends data, how can we solve this normally, or how can we solve this using MapReduce? Okay, so let's actually look at that. So how is the data or the friends data stored in a social network, in the case of a social network? So for every member, there would be a list of friends, right? So for every member, for example, A, there will be a list of friends like B, C, L, and ... For every member, for B, there will be another list of friends. And suppose we are assuming in this case, I mean, it doesn't really matter for this algorithm, but the case we are assuming is it's a symmetric case. If A is a friend of B, then B is a friend of A. But as we will see for this particular algorithm, this assumption does not matter. So suppose this is the way the friends data is stored. That means for every user ID, we will have a list of user IDs who are his or her friends. So suppose there are capital N members, which is a very large number. In case of Facebook-like networks, it could run into billions. Even otherwise, it can be a large number. And we'll assume it's a large number because we are interested in such scenarios. Otherwise, MapReduce and all are not required. And suppose every member has small n friends, and capital N is much, much greater than small n. Now, small n, how large can it be? So if it's like Facebook, it could be like 1,000. Or just a moment, I'll just take a call and come back here. Just a moment. Okay, so I'm sorry. We are back. You can hear me now, right?
Yes, sir.
Yes,
Okay. Okay. So, so suppose the small n is of the order of, let's say, 1,000 or 500 or something, and for simplicity, we'll assume it's kind of a fixed number. It doesn't really matter. I mean, you will see that what we are trying to do. Let's assume on an average, everybody has small n friends. It is just to give us an idea about the complexity, but the algorithm doesn't really need that everybody has same number of friends. So what would be a naive approach? So our goal is, given A, or for all users, so let's start with one particular user A. What we want to do is, we want to find out all other users with whom this particular user A has at least 3 mutual friends, or at least some K mutual friends, right? Essentially, what we need to do is, we need to figure out other users with whom this user has mutual friends. Now, in an interactive classroom, we could actually tell you to come up with approaches, but probably this will be the most common approach everybody will come up with first. So that approach is, folks, please go on mute. Amit, please go on mute. Okay. So that approach is, for every friend X of A. So for example, A's friends are B, C, L, and so on. So for all of them, each of them, okay, for every friend Y of X. So for example, if X equal to B, then for every friend of B, right, we will have to compute how many mutual friends that Y and A have. So that means, since, so basically we are looking at all friends of friends, okay, all friends of friends, and we are computing the number of mutual friends. If anybody is a friend of friend, obviously there is one mutual friend. But what we want is, what is the number of mutual friends, right? One mutual friend is not enough. So what is the number of mutual friends? So this would be our simplest approach for that. And then of course, we'll compute the number of mutual friends between Y and A. So to do that, we need to intersect the friend list of Y and friend list of A. Okay. So hopefully this is clear. Now let's think about how much time, or what would be the complexity of this algorithm, computational complexity. We are not thinking about network as of now. So what is the computational complexity of this algorithm? So for every friend X of A means we'll have order n friends. For each of them, there will be again order n friends, and compute the number of mutual friends between Y and A. So that means we have to intersect two lists of order n each, which is linear. You can actually, if the lists are sorted, you can intersect them in linear time. Okay. I'm not going to the detail of that. You can actually put a pointer in the beginning of both, and just move in the smaller one, and you can do this like a merge. So so you can intersect the friend list of Y and A also in order in time. So this means for every friend of X of A order n, within that another loop of order n, and within that another loop of order n. So this means order of n cube per member. And since you have capital N members, this is order of capital N times n cube. N is not very small. N is much smaller than capital N, but not very small. So this actually is a bad algorithm. I mean, rather, yeah, it looks simple, but if the data is large, it's not really good. All right. So what we will try is, we'll try to do something better. Okay, so a better approach, again, we have the same data. Better approach, we will still not think about MapReduce. We will still not think about the distributedness of the data. Let's think that, okay, the data is like this. Okay, and let's see what we can do. So now, for every friend x of a, and in this case, let's say x is b. Okay, so I mean, b is one example of such x. For every friend y of x, okay, so b, a is a friend of b in the other list. We'll write the triplet a y x. What this means is that x is a mutual friend between a and y, right? So this double loop essentially means x is a mutual friend between a and y, and we'll just simply write it out. So if we do this, what do we get? In this particular example, we get a b, that is the first one, then a g b, because b is a mutual friend between a and g. Similarly, a k b, and so on, right? So dot dot dot, and similarly later on, we'll maybe c is another mutual friend between a and g, so we'll get a g c, and maybe p is another mutual friend between a and g, we'll get a g p, and so on. All right. So now you are starting to get the idea where we're heading, right? So now anybody, please speak out. So anybody has a guess what should be the next step?
Find out mutual friends between them.
Yes. So how do we count, right? We need to count the number of mutual friends between a and all friends of a, friends of a, for example, g. And what we have done is we have written it out like this, right? But that doesn't immediately allow us to count the number of mutual friends between a and g. We have to do something, right? So what we have to do is, so the idea is similar to MapReduce. We'll have to perform the shuffle operation, or shuffle or group operation, right? So what we have to do, we have to sort or group. We'll use this terminology sort, group interchangeably sometimes. It doesn't really matter what you do. So now sort by the first two entries. That means sort by a y, okay? Which means we'll sort by the first two entries as something like a key. So then what will happen is we'll get all these AGB, AGC, AGP together, right? So obviously, I mean, every other group also, every other set of mutual friends also will get sorted. But in this particular example, we'll get this AGs, the first two entries, the same combination of first two entries will get together as a group. And that makes it obvious to count the number of mutual friends between A and G, right? So now all the AGs are together. So for each AY or AGs or whatever similar to AGs, we can count how many times it occurs, and that is the number of mutual friends between A and Y. Okay, so this is a better algorithm. Why? So let's actually look at the complexity again. So again, this is order n. For each friend x of A, this is also order n. We write it out. How much will this be? This is order n square, because there may order n square such triplets. To sort this, we will need order n square log n, right? So 2 log n square is 2 log n, so order n square log n. And once we have sorted, we'll again get order n square such entries. And then final pass, the counting will take one pass. It will take one pass to go through the whole list, which is already sorted by the first two entries, and we can simply count. So that count will take order n square. So it is the whole complexity is dominated by order n square log n per member. Okay. So what we have done here, we have not considered the distributedness of the data in any form, but what we have done here is we have kind of given it a MapReduce flavor, like writing out as key value pairs and then grouping and then counting, right? So we have done that. And looks like computationally also we have made some improvement. So now the question is, can we directly, apply this idea as a MapReduce algorithm? Okay. yeah, so instead of waiting for your answer, I would give you the clue that no, not so directly. The idea, I mean, in some way the idea can be used, but exactly this formulation of this algorithm cannot be applied to a distributed setting. Okay, does anybody have any idea why? Okay, all right, let's go on. So essentially this is the algorithm, right? So for each friend x of a, for each friend y of x, we write a y x. Now that is a problem if the data is huge and distributed. Why? Because it's possible that the friend list of A is in one node and friend list of friend of A is in another node, which means this particular nested loop is not possible. Just think of it, think of this again. I am looking at, so we can assume, let's say the friend list of A is in one node. Okay, that can be one line, one long line, right? So just a list of user IDs or something. So that is fine. That can be in one node, let's say we assume. But another friend list of B may not be in the same node. So when we try to say, okay, so for each friend x of A, that means, okay, now let's look at what are the friends of B. We don't have it in the same node. So in a if the data is distributed in a, for example, Hadoop file system, then we cannot do this. So we'll have to do something little bit differently, but we have actually got the idea what should be our key and what should be our value. Because here our goal is count number of mutual friends, and the mutual friend becomes the value because that's what we have to count, and the keys are or the key is the pair of candidate pairs. Okay, pair of user IDs who may have that mutual friend. So what we'll do is we'll see how this can be applied using MapReduce. So suppose in one node we have such friend lists. Okay, for some C we have a friend list, and another node we have another friend list. Of course, we don't have exactly one friend list in one node. We have many friend lists in one node. But suppose these two are in two different nodes in the distributed file system. What we will do is, but here we will not start with a particular user ID as a target. We will not try to find only friend suggestions for, let's say, C or something. Okay, so we will actually try to do as a batch. Let's say for all users. Let's try to do it for all users, and then if necessary, we can actually filter. So what can be our key and what can be our value? As we said, the mutual friend has to be the value, and the other two people it may connect are that pair is the key. So let's look at the friend list of the C, 2A, G, M, and so on. So here, what should be the key value pair or one particular key value pair? Okay, any idea?
BC.
Yes, again.
CBA.
BA. What BA?
Is hello.
No. So what is the key?
C.
CBA. No, I mean, C is not even anywhere in the second node, right? In the first node we have C, in the second node we don't have C.
So you can at least say this, no? C is a mutual friend between AG.
Right, exactly. So what we have is A and G. So every pair in that list, right? AG, AM, GM, they have C as a mutual friend. Okay. So what we have is for every member X, okay, fetch his or her friend list. So you work with one single friend list at a time because you may not have two different friend lists in the same node. But then within that friend list, for every pair, you emit the key value pair y1, y2, comma x. So for example, AG, C, AM, C, GM, C, and so on. So this you do for this node. And for all such friend lists, in this node you do that. For the other nodes, you do AGB, AKB, GKB, and so on, blah, 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 right? So if once you do that, it's again back to the same thing. Now our shuffle will give us, so this was the map, and then shuffle will give us all the AGs. You see that in the first map task has produced AGC, and the second map task has produced AGB, and maybe some other map task will produce some other AGP. So they will produce, they will group the pair of possible friends as the key and the mutual friends as the value. So once that is done, then the reduce is again simple. For each key XY, determine the count of mutual friends. So this is essentially a nice way to solve this problem. Yeah, so you see that if you look at the computational complexity per member, then this will be similar to the n square log n thing. That is probably the best we could do here. But in a distributed setting, we could not apply that algorithm directly. So, but the idea is the same. So for every friend list, every pair is the key, and the mutual friend is the person whose friend list it is. All right. So yeah, the rest of these we have already covered in the previous class. This is the portion which was remaining, so I covered it. I will again upload the updated slides. So what we will have in the end is one slide on MapReduce as a whole. Then you will have one short slide, set of slides on Spark. And today we are going to do a Jupyter Notebook session on Spark. So you are also going to have that. And there will be 3 different lecture videos in the website. All right, any questions as of now?
Sir, but in the latter case, the computational complexity is larger than the previous case, because
yeah, go on.
we have NC too many pairs for each friend, for each C and B. So
yes, so NC2 is order n square.
So, but in the previous case, we have linear time complexity.
Here, what? Okay, just hold on. Maybe is it my mistake? So for every friend x of a, for every y of x, we have this. Now this one. Okay, that's actually an interesting question. Although it looks to me that if you write out this for all members, okay, so let's think about this, and we'll have to come back. I'll have to come back to you in the next class. So yes, if you look at one particular list, you will have I mean NC2 pairs, and NC2 pairs, and you have NC2 times n such key value pairs, right? But on the other hand, here, if you do the same, oh yes, so that's actually not different. See, this we are computing the complexity for. This is per member, right? So this is order n square log n per member. And what you are doing here is you are actually doing it for all capital N members together as a batch. So here per list you have NC2 or n square order n square key value pairs. And for capital N such lists, you will get capital N times that. So ultimately it's the same thing. Okay, so if you divide the whole thing by capital N, you are going to get the same complexity. But okay, so here this is just to present the idea. Now one could probably optimize this further in case the goal is just to compute friend suggestion for some particular users and not the whole set of users in some batch. Probably then what you should do is, you instead of writing out the all key value pairs, you should write out only the key value pairs where I mean first the key value pairs for this AG, and then you know, do some kind of a filtering on the other key value pairs or something. But in a batch it works much more efficiently. So yeah, that's just the idea that what can be done in a distributed setting for all users in a batch. Okay, any other questions? Okay, if not, then what I will do is I will start the desktop. Okay, so now I'll share my desktop as a whole, and so that you can see the full, yeah, you can see the full flow. Let me increase the size of it here. So you see my terminal now, right?
Yes, we can see.
Okay. You see my terminal, I am into a particular directory and I'm actually typing PySpark. Now I have configured PySpark in a way so that it opens Jupyter Notebook instead of the PySpark, I mean the Python terminal in the terminal. There is an instruction in the notebook how to do that in case you want to do it. It's just for giving this presentation kind of thing, it's much nicer to use Jupyter Notebook. So let's do that. Okay, so it's opening this directory, and I have this PySpark tutorial.ipnb in my thing, and let's actually, yeah. So is the font size fine? Because you're all watching locally, I think it is fine, but just let you know. Maybe
Yes, sir, it's fine.
Okay. So, so PySpark is basically Python, but like you're using the Spark library. So to install and run PySpark on Jupyter Notebook, you can look at this. I hope it is, I mean, I made it a few months ago, but I hope this help will still be available. The main references for this tutorial are the Spark documentation itself. And I'm actually going to cover very simple things and basic things in this class. Spark, apart from the basic hello world kind of thing that we will do today, and some other small play around kind of operations, Spark definitely can do a lot more. Okay, so it has a very rich machine learning library, not deep learning essentially, but the traditional machine learning libraries, and it also has several hashing and PageRank and many other things implemented into it. We will cover many of those things later in the course, and whenever we do that, we'll come back and see how this thing can be done with Spark. Okay, so today it will be just a gearing you up on what Spark can do. All right, so let's start. So what we do is we start by getting the Spark context. Okay, so the Spark context, I call this SC. Okay, so the context is created, and this SC will do everything for us from now on. And in the last lecture, we talked about this resilient distributed data set briefly, or maybe we did it very fast. We will see exactly how this works now. So what these RDDs are, the RDDs are, an RDD can be created either from an existing collection in the driver program. That means you write something into memory and you can create an RDD out of it, or you can reference to some external storage system. Now, external does not have to be something alien. It can be my local disk, or it can be some HDFS file system. Okay, it can be even Amazon EC3. So essentially, Spark can plug into many file systems or storage. So in this case, obviously, we are doing something very simple, almost toy-like to start with. So what we are doing here in the next step is we are writing a Python list, okay, data 1 to 21, okay, and what I'm saying is, okay, this data, distributed data, we are telling the Spark context to parallelize the data. All right, so let's do that. So it has done it, and what it says is parallel collection at parallelize at Python RDD.scala 480 or whatever. Now, essentially, as I told you in the previous class, Spark just creates a lineage, right? It remembers how this was created, but it doesn't really perform any action as such until you tell it to produce some output. But we need to see what it did to parallelize it, right? So we actually gave it 21 numbers. Okay, so let's see what it did. So what I'm going to do, let me just check whether it's already saved somewhere. No, okay. So what I'm going to do, I'm going to save as text file. So this is a Spark command. Typically, when you are done, you want to output, you want to save your output, you use this save as text file. So this data.save as text file, I'm giving it a path. Okay, so it has done it. Okay. Now, what it has done, it has chosen a suitable number of partitions. It has chosen a suitable number of partitions. Now I'll go into my directory and see exactly what it has done. Okay, so this data1 is the directory. Okay, so I gave it save as text file user developio Spark playground data1, and this is where the data1 is. Now let's go into this data1. Now you can see there's a success file written, and then there are part 0002, part 007. So it has created 8 partitions of this. All right. So it has created 8 partitions of this. Let me actually look at what those partitions are. Let me go to another terminal. Okay, so let me go to another terminal, and this is Spark playground. So I have data1. Okay, so I actually have 8 partitions. So let's look at what these partitions are. So part 00000 is just 1 and 2. So similarly, I can look at all of them. So this is the first file 00. Oh, sorry. This is the second one 1 So there's only 3, 4. Then the third one is 5, 6, 7, 8, right? And then the fourth one is 9, 10. Fifth one is 11, 12, and so on, right? So as you see, it has created it has created 8 files, and it has simply distributed them. Now, another practical thing you can notice here is that Spark likes to go line by line. I gave it a list. It has not saved them as one number, then a space and another number and so on. So it has gone line by line. And this is actually one of the things that you will see in many other cases. Whenever we pass data, it will be stored, or it will like it line by line. And typically what we would assume is whenever it parallelizes things, it will not break the line into 2 lines. So if you pass it, let's say 1 million lines, or let's okay, so if you pass it 100 lines and tell it to divide it into 5 parts, it will, it may do 19, 21 and blah, blah, blah lines in one part, every part, but it will not break one line into and send it into 2 parts. So that is why if you want to make sure that a part of your data is actually in a contiguous place, it's a good idea to put it into one line. Obviously, it only makes sense if that one line is not too large, right? So you remember the blocks in HDFS. So one line should not be too large so that it exceeds the block size or something. But yeah, so it will actually not break the lines. And all those relations and tables we talked about, they are all treated as CSV files, comma separated files kind of thing, or tab separated CSV or comma CSV kind of files. Anyway, so that's not really important right now. We'll look at those usage of data later. So let's see. So this created 8 partitions. Now, can we control how many partitions will be created? Yes, we can. I can actually tell st.parallelize data, 4, and I save it to data 2. So let's actually look at data 2. So this is data 1, this is data 2. Now you see it has created 4 partitions. All right. So I can actually control how many partitions are created, and that's a good idea because then I know well how many map tasks can run together, right? So how am I going to parallelize? So it gives me something.
Sir.
Yes.
Sir, why can't we see the duplicated blocks in the partitions, because they have to be kept for fault tolerance, right?
Oh, okay. So in this case, Spark handles, in this case, we have not specified any of these things, and this is actually all on local. So we are actually not doing that. Save as text file is more like just saving as user output. Okay. If we, so this we are using for a standalone local mode. If we use some HDFS or actually distributed cluster kind of a thing, then the RDD will take care of that in a different way. Okay. So we will, I don't think we'll be able to look at that in a standalone mode, but it's, I will read up and figure out if we can simulate the replication factor within Spark while saving the file. So what Spark does is it tries to keep things in memory as long as possible. So unlike Hadoop, right? So unlike the vanilla Hadoop, what it does is it tries to keep things in memory as long as possible. So until you save it as text file, it will keep everything in memory. And within memory, it will, if you have a cluster, it will actually distribute things, and it will probably also do some kind of fault tolerance. But I believe there can be some parameter, just like this number of partitions, which can be set to instruct how it should do it. Okay, so yes, I'll try to figure out whether that can be also done. That can be also controlled in our local environment. All right, so here, of course, we are using the local file system. That's why. Now we'll have to learn two important things before we can apply MapReduce kind of algorithms in Spark. One is the lambda or anonymous function. So some of you, this has nothing to do with Spark in particular. This is actually in Python itself. So some of you may have used it, or maybe most of you have not. Have you all used lambda function in Python?
So most of us have, I think.
Most of us you have. Okay. So then if any of you have not, just let me know. Otherwise, I'm going to quickly go through this. So the lambda function is just an anonymous function. Instead of, when you have a simple thing to compute, instead of writing a separate function, for example, add A and B, right? So I can write it as a separate function. Def add 1 AB, return A plus B. And then I can apply that function. But if we simply, instead of giving it a new name, what we can do is we can also use it as a lambda function. Now this is what we have done here. Is really, I have basically given it a name again, but we'll see this. So basically, if you know lambda, the syntax is lambda. It's just a function. You give it A and B, and colon, this is the output. If you need to put in more code in there, you can actually do it with some parentheses and so on, but it's mostly useful if you don't have to put more code. It's a very simple kind of OR operation. And mostly the map operations are very simple like that, so we'll use that. So what we do here is we'll learn map also. Again, map is also there in Python. So recall that we already have defined this data. It's a list. Now, if we define this function square of every number, so square of a number will return simply the square. So that means if I pass it 2, it will return 4 and so on. Now, so what map does is it takes a function and a list as input and applies the function on every element of the list element wise. So what this will do, you map the function square onto data. That means it will transform 1, 2, 3, 4, blah, blah, blah to 1, 4, 9, 16, 25 and so on, right? So just stop me if you have a question, but otherwise I'm going to go through this a bit fast, hoping that you all know this. So what this does, it applies the map function on this list and we get a list with all the squares, element-wise squaring kind of thing. It's very useful for element-wise application of some kind of a function. And then we can actually use this whole thing using lambda with map. So map, instead of defining a new function name, we do lambda a goes to a square, and then we apply that on data. So we can actually do the same thing. All right. So I hope you all know it. Otherwise, please stop. Then the next thing is reduce. Now again, Python has reduce, although you have to import it from function tools. So what reduce does, okay, this is slightly different from MapReduce, but essentially it will do the same thing. So map works like, given a function, it applies the function on every element of the list. Given a function and a list, it applies the function on every element of the list. What reduce does is, given a function and the list, obviously the function has to be of the form that it takes two inputs and produces one. So here, for example, it takes A and B and produces A plus B. And now this, if you apply on data, what this will do is, let's look at data. It will take 1 and 2, sum them, make it 3, and collapse 1, 2 into 3. Then what we'll have, 3 and 3, collapse them into 6, 6 and 4, okay, sum them, make it 10, then 10 and 5. So what it will do, it will keep reducing the list by applying that function on every pair of elements, consecutive pairs of elements. So essentially what this means is that when you don't know how many, when you don't know the size of the list, instead of writing a for loop to aggregate things, you can actually write a reduce function to aggregate it. Essentially, we can actually sum 1 to 21 using, so sum the elements of data using this reduce function. Okay, fine. So next is, now we'll come back to Spark, having learned map and reduce. So Spark, as I said, is interactive, and we can see that it's interactive, but you can actually play around a lot with this. And some of those playing around is the following. So for example, if you simply want to print it on your terminal kind of a thing, so you do collect. Collect returns all elements of the data set as an array or list. Now, you should not use it if the data is large, because then you are going to actually call like millions of numbers or text words into your terminal. Not a good idea. We are doing it here just to show you how it works, and I have only 21 numbers. In the real practical case, you should not do collect. You should almost never call collect. You should save as text file and do the other things I'm going to tell you. But you can do first, that is the first element. So first element is 1. Or better, if you have a large data set, you want to look at, okay, show me, few elements of the data. So in this case, show me take sample with or without replacement. So in this case, let's say false, not without replacement, 5. So what this does is 2, 1, 9, 10, 10, 20. So basically it's taking a sample of 5 from our RDB. And I can do count also. Now, these things are all happening instantaneously. Now, in case we actually have a distributed file system and a large amount of data, all these count, sample, they will take some time, because they will actually call different nodes to give it the data. Especially count will definitely take time, because count will definitely take all the nodes to give their individual count and then sum them, right? So count will take time. All right, so there are many other things, and I will refer you to the.
Sir, is this count function using MapReduce engine to its code?
I don't think for this particular case it is doing, because it's just a small one. But it's actually, this data is divided into 8 parts. However, those 8 parts, because we are not using Hadoop, we are using Spark, those 8 parts are all in memory. Okay, we have saved them as text file, fine, but they're still in memory. So it is essentially taking count of all of them and then summing them. So in a way, it is doing some kind of a MapReduce, but all in local machine. So there is no network transfer, anything like that. Okay. So that's what it will do. So in a standalone mode, Spark will actually run multiple threads in parallel, but the network transfer is very fast, because we are actually not in a network. We are just swapping things within memory, right? So the network transfer or shuffle will be fast. So that is the advantage. Obviously, I mean, in a standalone mode, you can only work with a small amount of data. All right. So RDD from external files. So RDD from external files, let's say I actually have a file. This is the anarchism with page from Wikipedia. I have converted it into text. So this is lines, sc spark context.txt file. I give it a file and let's see what it does. It reads the text file. Now it has done very quickly because it hasn't actually read it, right? It hasn't actually read it, but I can take a sample and now it will give me 5 random lines from that page. And you can see some of those lines are actually blank lines also, which is possible. I mean, there may be blanks and paragraph breaks and all those things, right? Okay. I think I'll go over by 4-5 minutes to just give you the word count problem in MapReduce, just to finish it off today. So then let's do, having known all this, let's do the word count problem in MapReduce with Spark. So we'll create the RDD, right? So sc.txt file. At this point, it has done nothing. Okay, let's do a count. So it has 92,535 lines. Okay, it's a very big file. So many lines. Now what we'll do, we'll generate key value pairs. So our key value pairs were word comma 1, right? W comma 1. So for each word W, we'll send it to W comma 1. But for that, we of course need to split the strings into words, right? So every line is long text. We need to split it. So what we do first what we do is we say words equal to lines dot map. Now I pass the split function. Now this is slightly different from the way we use map on Python. In Python, I call map and then I pass a function and I pass the list. In case of RDD, I can actually call that RDD dot map. Okay, it is similar to Python, but it is this lines is in Spark RDD. So I call lines dot map, and then I simply pass the function. I don't have to pass the list because lines is my data. So I do that. So I map it, and I take a sample to see what it has done. Right. So what it has done, originally I had a list of lines, and now every line is split into list of words. Okay, so every line is split into list of words. So what I now have is lists of words, but that's not what you want ultimately. What you want ultimately is we just want a list of words. We don't want a list of words. So we'll instead use flat map instead of just map. So flat map is instead of list of word, a hierarchical thing, you flatten it up. So instead of just a map, we'll use flat map, and what that has done, I can actually take sample also. What that has done, oh sorry, I need to actually switch this off. Yeah, now you see the sample, I only have a list of words, right? So some of the words can be blank, or some of the words can look odd because I really haven't done any data cleaning, but well, I mean, we are just trying it out. So, so now what I have is I have converted my whole data set into a list of words. Now I need to perform the key value pair thing. So key val is words.map. So words, so remember RDDs are created from other RDDs by some operation. So lines was an RDD, words is also an RDD created by this operation. And because I am doing this text sample, it is actually also performing the action. Otherwise, it will not do anything. It will just remember, okay, to create words, I just need to do lines.flatMap, but I'm not doing it yet. Okay, but you know, to do this example, I'm actually doing it step by step. So it is actually creating all that. So next is key val. So key val is words.map. Now lambda word goes to w comma 1. Okay, so let's do that. So now you see that my junk words or blank words or good words all have gone to, it's a list of pairs word comma 1. And now I can do reduce by key in Spark. So reduce by key means since it is by key, it will actually group by key and then reduce. So again, I give the simple addition formula on lambda. Lambda m comma n goes to m plus n. So key val dot reduce by key. Okay, that gives me counts, and then we look at a sample of counts. Okay, it is actually doing it. So you can see upgrading, the word upgrading is present 3 times. Okay, this tumulus is present once, and all blah blah blah. All right, now this is what we did just to explain to you in so many steps. We can actually do the whole thing in, just a few lines of code. Once you are a little bit Spark savvy, you can simply call this. Let me just explain the code to you. se.text file this lines.flatMap lambda line goes to lines.split dot map lambda w goes to w comma 1 dot reduce by key lambda m comma n goes to m plus n. Okay, and then you save it as text file. So that's all. This is basically your hello world program on Spark. Okay, so let's just do that. Okay, and it has also saved as text file. Okay, we'll not do this Monte Carlo simulation now. Later on in the course, maybe we'll actually come back to this, or if you want, you can actually look at this. It's also taken from the Spark documentation itself. It's very interesting. But yeah, we'll come back to this later. I'll finish today's class just showing you what output it has produced. Anarchism counts, right? So anarchism counts. It has actually produced slightly distributed output. Okay, I need to go into this. So yeah, anarchism counts. And let's look at part 000. So you see anarchism is present 15 times, ease is present 14,931 times, and so on, right? So it has produced our word count output. It has produced it since the output was large, whatever Spark thought, it actually, so if you want to see the total, it has kind of divided it to 86,000 each, 86,000 something each, 2 parts. It has kind of already distributed it into 2 parts. It figured that, well, that could be, yeah, in fact, we can actually look at this. So both are 1.4 megabytes each. All right, so any questions on this? I will, of course, upload the Python notebook also here. I could do this in online Colab as well, but I wanted to show you exactly in local machines how it stores and all those things. So I did it in local machine. You will have to install Spark and PySpark and all those things if you want to do it yourself. We'll give some exercise later on. Yeah, I mean you can try installing things, looking at the documentation and all. Hopefully there will not be any problem. These are standard things you are using.
Mainly you install with pip, right? In
Yes,
Python.
yes. PySpark you can simply install with pip, and as far as I remember, I don't remember when exactly I did it, so I did it long time back. It will probably install Spark also, but if it does not, then you have to install Spark separately. So maybe just download Spark, keep it in a directory, and install PySpark separately, or maybe just pip will do the whole thing. Okay, it's like it will probably vary a bit if OS to OS, Windows, Linux, and Mac, and things like that. But you are going to figure it out. So, all right. So I think that's. Yes.
So on the face of it, it looks like all the map function, flat reduce, everything. It is being done as a normal Python code, right? Means we don't see any difference how it is done.
Almost, yes, almost. That is one of the reasons. It's slightly different though. In Python, as I said, the map has to be called map pass, and you pass the list and the function to it, and the function and the list to it. Here, these are RDDs. So RDDs are mostly things which I mean, the code looks like Python, and RDDs you can almost use them as Python objects. But yeah, there are certain things Spark has more to offer. So RDD, for example, count, take sample, and all those things. So in Spark, you always work with an RDD.
Yes, sir. Means for example, when we get that the words list, like from sentences, we split them and got the list of words.
Right. There we used only Python, right? So we basically used Python.
That was not saved in a distributed system, right? That was completely in my memory.
Yes. So you could get confused because I'm actually working with a small data on the local machine. Yes, it is completely in memory. But if it was actually to begin with in a distributed system, then the split will also happen individually on every node, and it will still be a large part of it will still be in memory as much as possible, but it will be in a distributed cluster.
Okay, means we don't have to worry about that much.
You don't have to worry about that much, exactly. So that is the point. So it's very user friendly. as long as you don't do any very bad programming, like you choose a key which tries to send every key value pair into one machine, that would be a bad programming, unless your program wants that, for example, or something. So unless you do something like that, you don't really have to worry much about it. Spark will take care of all those things. Okay.
Okay.
So we'll actually work with larger data later on, and practical problems. This was just a gear up thing, so we'll actually work with those things later on in the course. So yeah, so that's pretty much with the first topic, MapReduce and Spark, in the course. From the next class, we'll move on to the next topic, probably association rule mining, if I remember correctly. Because of one serious problem in the family, I missed the last the doubt clearing session. So if Monday is okay with you, Monday 2 o'clock, then I can actually host it then. Is Monday fine? Monday 2 o'clock? Okay, just somebody, the class representative or somebody, drop me a mail if Monday 2 o'clock is fine. Then I will create a Zoom meeting. Whoever wants to join, I will be present.
Sir, will it be possible to start the? Will it be possible to start the class from 2:15 onwards, because some of us have lunch?
Oh yes, yes. I have no problem. I mean 2:15, 2:30, whatever you say.
So how long is this?
Okay.
It's just an optional doubt clearing session. If you don't have doubts, you don't join. I mean, if you have any doubts in this topic, it's just because we are not meeting in person, right?
I mean, some of us have class at 3 o'clock.
We can do from 2:15 to 2:45. If you have any doubts, you can join at 2:15.
Okay,
as soon as your things are cleared, you leave.
Okay, you can leave. Okay,
it's all
fine.
optional, right? So you don't have to join. It is just if people have doubts, we'll have a half-an-hour session. I don't think there will be too many doubts right now.
Yeah.
So let's do it then. 2:15 to 2:45 on Monday. Just for this week. For next week onwards, we'll do it Friday sometime.
Fine.
All right. Okay. So thank you all, and as usual, I will